Alright, we're looking at this lecture that's called Models of the Atom. The quote we have is: "The unleashed power of the atom has changed everything, saved our modes of thinking, and we thus drift towards unparalleled catastrophe." It's from Albert Einstein. So we're going to look at the atom and how we know what we know. The learning goals for this lecture: the students will be able to understand the experimental design, result, and analysis that led to the various models of the atom. So basically, we're going to look at all the scientists and each particular part that led to our model of the atom that we know of now. And then, secondly, we'll understand the progressive nature of science theory. So, in looking at these different theories and how we're becoming more and more precise as time goes on with our scientific theory. So, what we already know and what we should know coming into this is that atoms are the smallest particle that retains the chemical and physical property of that element. We know that atoms are very, very small, and that atoms are made of protons, neutrons, and electrons. And we call these protons, neutrons, and electrons, we call those subatomic particles. Now, what we should have learned in the lab and just looking at different things: number one, that changing the protons changes the identity of the element. So, as we added protons into the atom, we changed the element. And the charge and the mass. And so there are three things that change with a proton by adding protons. Changing the number of neutrons just changes the atomic mass. And then changing the electrons changes the charge. So if we have more electrons than we do protons, we have a negative charge. If we have less electrons than we do protons, we have a positive charge. And we would call this, when it has a charge, we call that an ion. And we'll talk a little bit more about that later, but we'll just introduce it here. Now, the first person we're going to look at is Dalton, and we're looking at Dalton and the experiment that he did. Now, what Dalton did was Dalton mixed gases in various amounts, and so he dealt mainly with gases, and he predicted that gases would combine in different ways to form new products. And so we're looking at this, and what we're seeing is that in Dalton's model, we have these different gases combining to form in different ratios. But again, what we saw in Dalton's experiment is that they combine differently, but we saw the law of conservation of mass. So all of those will combine, but will still keep or retain the same mass. And what this did was it led Dalton to look at his analysis, and Dalton postulated the following things. He postulated that elements are the smallest particles. Elements are small particles called atoms. So he was introduced atoms. It was introduced previously before this, back in the Greek philosophers, but he was the first person to kind of talk about it in this sense, that in very defined terms. Secondly, that all atoms of an element are identical, that atoms cannot be divided, created, or destroyed, and that atoms combine in whole number ratios to form new substances, and atoms can be combined, separated, and rearranged. And so this led Dalton to his theory, and some of this wasn't precise enough for what we'll see later on, but this was the first postulate of the atom, and basically the five things that Dalton talked about. So Dalton's model of the atom, so what he kind of thought of is that it's composed of elements, that it was indivisible, and it was spherical. And so Dalton kind of thought of it as just you can think of it here kind of as that marble, that they were small little spherical objects that couldn't be broken up, couldn't be divided, which we'll again look at later and see that that wasn't entirely correct. Then we move on to the next scientist. So later on, further down the road, we see that Thomson did an experiment with cathode rays. That basically what he did was it was an electron beam, There's an electron beam, and it can be produced by subjecting a gas to a large voltage. Cathode rays were originally used in TVs, very early TVs, and they have a gas inside a tube, and it's heated up. And what he did was Thomson fired cathode ray tube between two charged plates, so a plate here and a plate here. When I mean charged plates, I mean there was a positive plate and then there was a negative plate to get that charge. And Thomson knew when he looked at this, you would have this cathode ray kind of going in through here. And when he would charge the plates, what he knew is they knew that opposite attracted. And what would happen is this cathode ray would bend. And it would bend specifically toward the positive plate. And so what Thomson was able to do then was Thomson said that atoms can be divided into smaller parts, constituents, basically smaller pieces, and that atoms are electrically neutral but have a negative charged particle called an electron. So Thomson was the first person to coin the term electron and basically use it and have scientific evidence to back it up. And so therefore, since an atom must be neutral, then there had to be a charge, a positive charge, to kind of balance everything out. But what we see is that Thomson discovered the electron, and he just did this by having that cathode ray go through this tube, and it would tilt up towards the positive end. And so he said there had to be something negative, and since all atoms are neutral, or most atoms are neutral, the ones he was dealing with, they were neutral, there had to be a positive to help balance it out. And so Thomson created and built on top of Dalton's model and built his model of the atom. It's referred to as the plum pudding or chocolate chip cookie model. That's how you normally see it. And what he thought was that he had negatively charged particles, and that would be represented by the red dots. And it was just floating in this positively charged mass. And so he thought basically that these little red dots just existed here, and they just floated in this positively charged mass, which balanced out the charges and made them neutral. Then moving later on, discovering just a little bit more about it, we have the Geiger-Marsden, or the Rutherford. This is more commonly known as the Rutherford gold experiment. And what Rutherford did, or Geiger-Marsden, those guys, they shot alpha particles. And so an alpha particle is just a helium atom that's charged, it's an ion, and they shot it at a piece of gold foil. And this was no ordinary just piece of gold. Gold is so malleable, meaning it could be pounded into very, very thin sheets, that it was a piece of gold foil that was just a very few atoms thick. So it really wasn't that thick at all. And they shot alpha particles at it, as you can see here, shot alpha particles. And what they were seeing is if it was going to react like the plum pudding model, these alpha particles would just go straight through it and maybe bend a little bit to try to get away from the negatives, but not much. And the alpha particles were fired at the gold with a detector, so this detector screen was around it. And so they were seeing where the alpha particles were going to go. And they were going to measure the deflection, how much these alpha particles bent. And so what they saw in the results of this, the data was shown, or down here shows the average per 8,000 trials. And you can see that 7,200 of them would go through with absolutely no deflections, but 799 of them would go through with partial deflections, and then you would have one particle that would have a major deflection. And so what we see is that we have the majority of them would get through, some of them would be a little bit deflected, but one particle would basically bounce back. And this led Rutherford to discover basically the nucleus. And so as the alpha particles would travel through, the majority of them would just travel straight through, but then there would be one in about 8,000 that would bounce back, that would hit this nucleus in the middle. And so this led Rutherford to discover the nucleus. He said that the nucleus was the positive charge of an atom. It's very dense, and in a very small area, and we call that the nucleus. So it's positively charged, it's very, very dense, and it's a small area in the middle that we call the nucleus. The majority of the mass of an atom is in the nucleus. So when we look at the mass, we look at the protons and we look at the neutrons in the nucleus, and we'll talk more about neutrons in just a little bit. But all the mass is going to be in that tiny little center in the middle. And the majority of an atom is basically just empty space, because the majority of those alpha particles just went straight through with just minor, not even any deflections, and then about 799 of them went through with a little bit of deflection, and only that one particle bounced back. So basically the majority of the space is just empty. So Rutherford model of the atom, it's often referred to as the planetary model of the atom. That we have the positive nucleus at the center of the atom, and the electrons move around the nucleus at a variety of distances depending on the energy of the atom. And so basically you'll see they kind of just orbit around, but they're not really set in a very specific place or a very specific distance. They just kind of move around the very dense nucleus. Then we get even further down the road and we see that we have Bohr. In Bohr's experiment, it was glass tubes are filled with a gas. The gas is subjected to a very large voltage, and that high voltages produce light. And what we see in this light is they produce a very specific pattern. So what they saw was, you can see these lights here, is that it produced very specific lines. So each element had its own unique specific lines for each one. You can see we have one here for helium, and we have one here for hydrogen, mercury, neon, and sodium. And so in looking at this data, basically we had a very unique fingerprint of each element. And this led Bohr to theorize that every atom produces a consistent and unique spectral pattern. So basically each atom has its own little thumbprint or fingerprint that it can be known by. And most elements produce very few colors, and that the electrons must have discrete specific energies. And so what this led to the Bohr model of the atom, which we've probably seen before, that basically the electrons orbit the nucleus, so they kind of go around in these circles, and that electrons must travel at a very specific distance from the nucleus. And these distances are called orbitals. And then absorbing energy causes electrons to move higher, and then as they come back down they emit light. So we talked here, when we talked about Dalton and the law of conservation of mass, well, this is a law of conservation of energy. If an electron goes up and absorbs energy, when it comes back down it must emit energy, and that's what those lines are. It's when an electron drops back down its energy level and it emits light. And it emits light at a very specific color depending on basically the distance that it falls. So let's look at some examples. When we're looking at this first one, it says, which of the following is the most accurate model of the atom? And justify your answer using the clear method. Okay, so when we're looking at this, we would say that the Bohr model of the atom is the most accurate model, and is incorporate evidence from Dalton, Thomson, and Rutherford, and that the Bohr model includes electrons orbiting at discrete energy levels, making it more accurate than the models with continuous energies as shown in the line emission spectrum. So when we're looking at this, basically what we're saying is that Bohr would be the most accurate or the most precise model, because it incorporates all the other models and it has reasoning for all the other models. Our next one, it says, explain how our model of the atom would differ if the results of the Geiger-Marsden or the Rutherford gold experiment would have resulted in the following. We would have 8,000 with no deflection, 0 and 0. And this basically what it would tell us is the result would indicate that the nucleus is either much smaller or that the nucleus doesn't exist. So if there was no deflections, we would basically say that it doesn't exist, and we would basically say that the plum pudding model, or the chocolate chip cookie model would probably be the correct thing, and this would support the previous model. But we didn't see that. Obviously, we saw some deflections, and that's where Rutherford got the nucleus, discovered the nucleus, and then was able to determine its properties. Now, we've been talking a lot about all the different things, so let's talk about the subatomic particles. We have three subatomic particles as protons, neutrons, and electrons. Now, there's a few things that we need to know about protons, neutrons, and electrons. Protons are positively charged particles. They are found in the nucleus. They have a very large mass, a very small volume, and it determines the identity of the element. So when we look on the periodic table, we look at the atomic number. That is the number of protons, and it determines the identity of that element, what it is. Now, the electron, on the other hand, the electron is negatively charged particle. It's found in orbits around the nucleus. It has negligible mass, meaning it's so small in comparison to a proton that it doesn't really matter. And then it moves in a large volume but occupies very little space. So they move around the nucleus in a very large volume, but they occupy very little of it. And then the difference in protons and electrons determines the charge. So if we have 4 protons and we have 3 electrons, that means we're going to have a +1 charge because there's more positives than negatives. Okay. Now, moving on from here, we've talked about our protons, neutrons, and electrons, and we talked about each experiment. We see that with the Thomson model that we discovered the electron, and then we saw in the Rutherford gold model that the nucleus was found. And then in the Bohr model, where we have the different specific energy levels. But what they noticed about the atom is that the atom, they could calculate the number of protons, and they would find out that the mass was different than it should have been. So basically there had to be something else there. And so Chadwick did an experiment where polonium gives off a type of radiation called alpha particles, and you can see that these particles collide with the beryllium, and the particles appear to come off the beryllium and collide with the paraffin. And so basically we have this setup where we have the beryllium and we have the alpha source, and it's going through it and it's colliding with the paraffin over here. Now, what's actually colliding with it and what's happening is that you see the particles that are coming off are going to be the neutrons, and this is how the neutrons were discovered. So the analysis of it, that there is an electrically neutral particle. So as those alpha particles went through it, it bounced off a particle, and they were very neutral particles in the atom. That the particle has a mass similar to a proton, and the particle is capable of being converted into a proton. The particle resides in the nucleus. And so Chadwick, what he discovered by firing those alpha particles at that polonium, basically what happens is that he discovered the neutron. And that was our last subatomic particle that we have that was undiscovered, and which accounts for the mass that we have. And so we're left with the model of the atom that we mostly use in this class. We'll critique it just a little bit more, but for right now, we have the neutron, that neutrally charged particle found in orbits around the nucleus. No, it's not around the nucleus, it's in the nucleus. Relatively the same mass as the proton, and it's located in the nucleus. So the model of the atom that we have protons, neutrons, and electrons are together in the nucleus, and that the electrons surround the nucleus with distinct energy levels called orbitals. And so this is the model of the atom that we have all the way up till Chadwick.